All right, welcome back. So this is Unit 4, Contextual Applications of Differentiation. So this is the first of our 2 units referring to applications of the derivative, how we can use this. So anything from Units 2 and 3, talking about your polynomial derivatives, your trigonometric derivatives, exponential logs, basic power rule, your product rule, quotient chain rule, all that kind of stuff, implicits, multiple derivatives, all that's going to start getting applied now. So you'll typically find in most places, most teachers' classrooms or the AP and things like that, you'll find that if you only need to find a derivative, it can be a fairly complicated problem. But if you're going to use the derivative, typically they'll use it in a slightly easier version of that. So you'll still see basic chain rule, but it won't be anything too crazy. You'll see mainly polynomial functions, e-raised like, the 5x squared kind of power, sine of like 2t squared, things like that are not overly crazy because you're going to need to take the derivative and then use it to do something else. If they do want you to work with a very crazy, complicated derivative, most teachers, and again the AP, other types of classes and programs, will tell you here's the derivative already, and then you use it for whatever purpose you're trying to do. So first up with this application, the idea of straight line motion with a derivative. So this is the connection to physics. This is talking about position, velocity, and acceleration. Position is just your regular function, and then velocity is the derivative of position, and the acceleration is the derivative of velocity, which makes it the second derivative of position. So this particle is either going to move horizontally or vertically. We're not going to describe it as moving in both directions at once typically, but it would be a horizontal or vertical motion. So here's our position function, s of t. We'll want to find velocity and acceleration. So velocity is just simply a derivative. We'll get 27t squared minus 8t. And then plus 3. The 1 disappears. And then acceleration is the derivative of velocity, so it'll be 54t minus 8. This time the 3 disappears. We're not going to find any further derivative besides that. Velocity is first derivative, acceleration is the second derivative. Going backwards, we'll talk about that, how we can work backwards from acceleration to position when you get this up with units 6, 7, and 8. Now, we might be asked to find the velocity at a particular point. So there's 2 ways of doing this. The long way is to find the actual velocity function. So v of t would be 8 minus, well, this is a product rule right here. So minus 10t cosine t minus 5t squared times a negative sine t, which would simplify down to just simply be 8 minus 10t cosine t plus, because the double negative, 5t squared sine t. And then you substitute the value of 2 into that, and then you would find, if you work that out, you'll get 34.5089, which is perfectly fine. But you're really not going to want to do that for a lot of these kind of questions, so we can use our n-deriv tool. So if you remember, we talked in, I believe, Unit 2, we talked about finding the numerical value of the derivative using your calculator. If you have to refer to my calculator playlist for using the n-deriv numerical derivative, feel free. Stop this video, go to that, watch it. But you can go to your math, option 8, n-deriv, and you can do it all in one step, and I'll give you the exact same answer, 34.5089. In both cases, as always with calculus, make sure you are in radians mode rather than degrees. You will not do any of these problems correctly if you were ever in degrees mode rather than radians. Okay? So that's using the velocity and the calculator to help find the value there. We can do the same thing if I want to find the value of acceleration. We can use the n-deriv tool, but we need to know what the velocity is. The calculator is not capable of doing that second derivative like that. Well, at least in that way. There's ways around it that you can use it, which we'll discuss that in the calculator videos. Now, one important thing is the idea of the average velocity and acceleration, which are not actually derivatives. These are based off the average rate of change, which is a slope, which is what these 2 formulas are. The slope y2 minus y1 over x2 minus x1. So average velocity is the rate of change of the position over the time, whereas the average acceleration is the rate of change of the velocity over the time. So if we want to find average velocity of this particle, we're given position, we'll need to know what s of 6 is. So 6 times 6 squared minus 3. 216 minus 3, which is 213. And s of 1, 6 times 1 squared minus 3, which is 3. So then our average velocity would be the s of 6, 213, minus s of 1, 3, over 6 minus 1, and we get 42. You're also welcome to do s of 1 minus s of 6 as long as it's 1 minus 6 on the bottom. So it's like anything else with your slope. As long as the order is staying consistent, it will not matter, it will not affect things. All right, so that's our average velocity. The key is we're not actually finding the velocity function. Yes, the velocity function is 12t. Great, not what I want to know. Okay, that would be more referring to the instantaneous value of the velocity. The slope of the tangent line, all those kind of things are referring to the derivative. Average velocity is simply an average rate of change. Average acceleration, same thing. I don't want the actual acceleration function. I use the velocity function to find the average rate of change here. So if I was starting with position, I would then take its derivative to get to velocity and then do my average rate of change. So I'll need to know the velocity at 5. So negative 6 times 5 cubed plus 1 is going to get us a negative 749 when we finish calculating it out. Velocity at 3, negative 6 times 3 cubed plus 1 is going to give us a negative 161. So our average acceleration would be the negative 749 minus a negative 161 over 5 minus 3. Get negative 588 over 2, which is negative 294. We weren't given any units for the problem, so we're not really worrying about units for right now, but keep in mind velocity would be a unit kind of like length per time, so like feet per second. Acceleration would be a length per time squared, so it would be like meters per second squared. Those would be like the equivalent time units you could use for velocity and acceleration. Now, the object, when it's in motion, we have it moving either left or right for positive and negative directions, though obviously it could be moving up and down instead. Typically, we'll talk about it as a horizontal direction as just generic, but it can move wherever we want. It also could be at rest. All this is based off the value of velocity. When velocity is 0, the object is rest. When the velocity is positive, the object is moving to the right in the positive direction, whereas when the velocity is negative, then it's moving left in the negative direction. So if it's moving up and down, going up is a positive velocity, down is a negative velocity. It just depends on the orientation of the object itself and which way it's moving. Now, in addition to whether it's moving left, right, or at rest, we can talk about the speed of the object. So if I want an actual value for speed, it's the absolute value of the velocity at that spot. So if velocity was negative, yes, it's moving left, but the speed is going to be an absolute value, not always a positive value. Now, whether or not the particle or this object is speeding up or slowing down depends on both velocity and acceleration values. If you think of both velocity and acceleration as a vector, where we're talking about the direction, if they're both pointing in the same direction, they're both positive or they're both negative, the particle will speed up. You can think of it as the acceleration's helping velocity make it go faster. Whereas if they're pointing in opposite directions, one positive, one negative, they're going to be fighting each other, the particle is going to be slowing down. Okay? So make sure you're careful with the context of the question it's asking. If they want the actual value of speed, absolute velocity, and that's it. If they want to know the concept of speeding up or slowing down, look at the velocity and acceleration values and see whether they're going in the same direction or opposite directions. So for example, we want to find when this object is moving left, when it's moving right, so we need to know when is it equal to 0. Now this particular function right here is not something that's solvable in terms of factoring, so you're going to want to graph this. Okay, so your calculator, you're going to take it out, you can go to your screen, go to y equals, shouldn't have to review how to graph, just use x instead of t in the calculator, so 8x cubed minus 5x squared plus 3x minus 4. I will recommend that your window, you change your x min to be 0, because x is being used as the t there, and we can't have negative time. So if we look at that particular graph, you will see your graph will look something like this. That's all your calculator screen will show you. Even if you were to attempt to zoom out to something truly absurd, you're not going to see any sort of actual difference besides just that one spot where it's crossing over. So we don't need to really worry about anything too crazy there. Now, we can use this calculator again to find the value of where we're crossing the x-axis right here, essentially the t-axis. So we do our zero calculation. Again, if you have to review how to use the calculator to find this kind of stuff, again, stop the video, go to the calculator playlist, and go through how to find the zero for a location. So you'll find that this value right here is at t equals 0.8624. So that's where we cross the horizontal axis. So what's happening here is this means the velocity values are negative before this and positive after it. Again, negative velocity means we're going left. Positive velocity means we're going right. So we're going left from 0 to 0.8624, and then we're going to go right from 0.8624 onto infinity. Now, if the graph showed more dips, where it kind of went up and then down and up and down, kind of crossing it multiple times, we'd have multiple points where it's changing the direction. Here, there's only that one spot. So in general, you set the velocity equal to 0. If it's a simple enough equation, you can solve it by hand. If it's more complicated, you graph it and see visually where it crosses. Just always make sure your x min is always 0 for these time questions. Now, you might not be asking for, in general, what's happening left or right. They might be saying at one particular location. Is this thing slowing down, speeding up at 2, and what's happening? Which direction are we moving? So the direction needs the velocity. So the velocity at 2, you would just plug in 2 into this equation, 9e to the negative 3 times 2 power, plus 6 times 2 squared, sine of 2. It's obviously a calculator-based thing. You can't do e to the negative 6 or sine of 2 by hand. And you'll get a positive 7.9267. So that means we are moving right at time t equal to 2 because your velocity at 2 is positive. Now, whether or not it's speeding up or slowing down, we know velocity is positive, but we need to know what acceleration is. So acceleration is the derivative velocity at 2. And again, we could take a algebraic derivative there. It's a simple chain rule for e, simple product rule for the 2t squared sine t, but we should instead use our n deriv option. So go back into your calculator, do your math, n deriv, type in the equation at 2, and you should be getting the value of positive 3.8783. So because both v of 2 and v prime of 2 are positive, this thing is speeding up. Okay, so obviously if you were doing something more, you had to write, like for a teacher, the justification, the explanation, do a more complete sentence right there. Don't just simply say they're positive, speeding up. They're positive, this tells us that we're speeding up, some version of that. But again, the key is they're both the same sign. So if they're both positive, we speed up. They're both negative, we speed up. They're opposite signs, one positive, one negative, we slow down. That's what's always going to happen. All right. Now, there'll be times you'll be given the graph already. So they tell us the particle P moves on the number line. The graph of position shows S equals F of T, shows the position of P as a function of time. So this is a position function graph. When are we moving left? When are we moving right? When is it at rest? So again, we need to know what velocity is. So velocity would be the derivative of position. Derivative of position, in this context right here, means the slope. So we'll notice from 0 to 1, we've got I'll change different colors here. We have a positive slope. We have a 0 slope. We have a negative slope, 0 slope, and then a negative slope. So for part A, where is it moving left? Well, where's our slope negative? Our slope is negative from 2 to 3 and 5 to 6. So that's where we would have this particle moving to the left because of the negative slopes. Where is it moving right? Well, that's where we have a positive slope. That would be just from 0 to 1. And where is it at rest? At rest is when the slope is 0 because that's when the velocity is 0, which would be from 1 to 2. And again from 3 to 5. So that's how you read the graph of a position, when the particle of the position is given to us. We're looking at the slope values. Where are we positive? That's where we are moving right. Where are we negative? That's where we're moving left. And where are we 0 flat? That's where we're at rest. All right. We also will have graph of velocity and asking similar types of questions. Talking about where is it moving left, where is it moving right. So now we're given the graph of velocity. Moving left is based off when velocity is negative, which would be below the x-axis. So we're going to move left from 1 to this exact value right here. We kind of need to calculate that out. It's a linear line. The slope of that line is a positive up 1, 2, 3, 1, 2, 3, 4. So that line's got a slope of 3/4. So I can write my equation as y using this point here, 6, 1. So y minus 1 equals 3/4 times x minus 6. So we want to know what's the value of x when y is 0. So that gives us -1 equals 3/4 x minus 9/2. So 3/4 x would equal a positive 7/2. So x, when we multiply by 4/3, is going to be 14/3, which is 4.6 repeating. So move left from 1 to 4.6 repeating. And that's it. It's going to move right from 0 to 1, because that's where it's above, and then again from 4.6 repeating until we get to 7. So again, we're not looking at slope here because we're given the graph of velocity. So we already have the velocity. We're looking for the velocity values are positive or the velocity values are negative. Now for part B, when asked about acceleration, this is where we're looking at the slope now. So we can see we've got a negative slope from 0 to 2, a positive slope from 2 to 6, and negative from 6 to 7. So acceleration is positive from 2 to 6. Acceleration is negative from 0 to 2, and then 6 to 7. All right, so again, you have to be very careful. They're going to tell you in the very beginning of the problem what type of graph you're given. Are you given the velocity graph? Are you given the position graph? Are you given the original function, a derivative function? And you have to be able to interpret that. We're going to talk more about interpreting graphs in Unit 5. Will just be more generic function graphs we'll be interpreting. But for right now, these graphs are based on the position, velocity, and acceleration. Now, when does the particle have the greatest speed? So we're not talking about speeding up or slowing down. That's part D. Greatest speed is the absolute value of velocity. So the highest or lowest point overall, the highest point is at the positive 2, lowest point is at the negative 2. Those are both the same then, because the absolute value of -2 is 2. So this would occur at time t equals 0 and t equal to 2. Because they ask, when does the particle have the greatest speed? If we want to know what is the greatest speed, then it would be the positive 2. They didn't give us units, it looks like. Well, they might have. I kind of took this out of a textbook and cut it off, looks like. So it looks like it's based off seconds. Let's say it was feet. So if they want to know what was the actual greatest speed, it would be 2 feet per second. Now, final parts. When is it speeding up? When is it slowing down? So speeding up versus slowing down. So speeding up occurs when velocity is positive and acceleration is positive, or velocity is negative and acceleration is negative. So you'll see from 0 to 1, the velocity is positive, but the acceleration is negative because it's a negative slope. So that means it's going to be slowing down. 1 to 2, velocity is now negative because we're below, and it's still decreasing line, so the acceleration is also negative. They're both going the same direction, so we're going to speed up. And then from 2 to that 4.6 repeating, we are now a positive slope line, but we're still below, so we're going to slow back down again. So that's from 2 to 4.6 repeating. After the 4.6 repeating, we're now above it again, still going upwards, so it's going to start speeding back up again. 4.6 repeating until we get to 6. And then from 6 to 7, again, velocity is positive, but the acceleration is negative. So you have to, again, look at both pieces of this puzzle to be able to answer the speeding up, slowing down question. Obviously, it's a little bit easier to do mathematically with actual numbers, but again, when they give you the graph, you just need to be able to visualize above the x-axis, velocity is positive, slope is going down. That's why the acceleration is negative. That's what's happening from 0 to 1. Then we apply that same process to the whole thing. All right, so this is just simply a piece of the stuff you can see with position, velocity, and acceleration. This should give you enough to answer any other questions you could see with this stuff. Again, everything else we're doing in this unit is all about applications. How can we apply the derivatives in some way to do other things? So I'll see everyone next time for 4.2.